Okay, let's start. Let's start with problem 1, an integer equation. So this is a little bit about number theory. Let's get started for the question I. So we know that question I is very symmetrical. We don't really have to change it to other form, even though we can. We can change it to something like AB plus BC plus CA equal ABC. And for this form, actually we can do a little bit factorization. We can do factorization to something look like this: a minus 1 times b minus 1 times c minus 1 equal a constant. You see, if you expand this part, it will be abc minus ab minus bc minus ca, and you also get a plus b plus c, so this will not actually work directly. In fact, let's look at this equation. 1 over b plus 1 over a plus 1 over b plus 1 over c equal 1. This is quite tight, actually. We can try to plug some numbers in and let's see how tight this equation is. We have really strict requirements of ABC. They are positive integers. So since they are very symmetrical, without losing any generality, we can let A is less or equal than B, B is less equal than C. And to start with, if we set, so we can discuss A from the smallest positive integer, which is 1. And we have a general idea before we discuss into real cases that if A gets really huge, A gets to a huge number, and since B and C will be only larger than A, and A, B, C are all on the denominator, the left-hand side will be very small. Of course, it will be smaller than 1. So I think we have a rough idea that we can just finish all the possibilities with bare hands. Okay, let's go. So let's start with A equal 1, and this is clearly impossible because 1 equal 1 and B and C cannot be 0, of course. So it's impossible for A equal 1 cases. And we said A equal 2. That is turning to 1 over 2 plus 1 over B plus 1 over C equal 1. Let's just say 1 over B plus 1 over C equal 1 over 2. And for these, we can continue our discussion. So obviously we cannot set B equal 1, and we cannot set B equal 2. We can only set something like B equals 3. So from B equals 3. Let's use a different color. If we set B equals 3, we see that this doesn't really work. In fact, so for this, actually, we have another method, which might not be fast, but that is very systematic. We don't really want such partial or like this kind of form. We transfer it to something like B plus C equal 1 over 2 BC. Okay. And this we have BC minus 2B minus 2C equals 0. And we can do a little bit of trick to solve this kind of equations. We can do B minus 2 times C minus 2. You see, if we want to expand this, it's BC minus 2B minus 2C plus 4. That's 4. And we can solve this by looking at this equation. Since we have B is smaller than C, and these two are symmetrical, this can only be 1, 4, and 2. 1 times 4 and 2 times 2. This gives us, so this actually gave us BC equal 3, 6 and 4, 4. No other solutions, of course. And So for now we have, so for a equal 2 we have 2 solutions. But this is a very systematic way to solve this kind of equations with multiple variables. We convert them into multiples, so one multiplied by the other. Then we can just use this kind of thinking method, but actually this is not necessary, since if we just look directly at this equation, we can see that b cannot be 2, so we start from b equals 3, and if b equals 3, the c will be only c will be 6, and if b equals 4, c will be 4 as well, and if b is equal 5, we can see that first we are sure that c is larger than b, so the best possibility for the left hand side is c is equal b. So but 1/5 plus 1/5 equal 2/5, which is still smaller than 1/2. So I think here we can use a restriction we set for ourselves, that is b is always more than c. So 1/b plus 1/c is smaller than two over b, and we want to find the one when the b actually doesn't work, so it's when it is more than 1/2. And this is quite obvious. It's directly point out that it's when b is larger than 4. Then whatever you choose, you cannot meet the requirements. I think this way to solve it is very useful, because you can quickly show that there are some sort of limits. But I mean, this way you factorize the equation can also make the solving process more systematic. Let's go on. So f equals 3, so that was 1/3 plus 1b plus 1/c equal 1. C plus c 1 equals 2. We use the same method. Sorry. 2 c1. It's 1. So 1b is larger than 3, it doesn't work. That is weird, because if you're looking at that, so this is interesting. Therefore, we find out that b can actually only be 3, because we require b should be at least 3. B should be larger or equal than a, and a is 3, and b should be larger than 3, so b can only be 3. And when b is 3, we find out that c is 3. So the only solution for this is ABC equal 3, 3, 3. Let's look at a equal 4. And actually we have a sort of instinct that 8 equal 4 is not going to work at all. Let's check a equal 4 still. Let's repeat the same process. This is what I say, this factorization might not be necessary, because we don't really need that, okay? 1/b plus 1/c equals 3/4. And yes, to know when it is 3. It's more than 3, which is actually it is apparently smaller than 4, so this case doesn't really work, because we need ABC to be in an order that we want. So I think for now we have already ended all of our discussions. We have got very limited options. And then for the left, it's about rearranging the solutions. But the only available or valid solutions should be the ones we come up with above. Okay, so that's, I would say, the end for question 1. And let's write the hence part. Hence C equals, we know 1 is not possible, so it's 2, 3, 6, 2, 4, 4, and 3, 3, 3. Okay, so let's look at question 2. You see that it is converted from an equation to inequality. So actually it's the same for inequality, because you see that inequality, it's still very strict requirement. When A, B, C, these positive integers, they are getting bigger. When they are getting bigger, the left-hand side is going to be extremely small, and no longer they are going to satisfy the requirement, which should be larger than 1. So this is very strict, very tight, you know. But I think we can still try to adapt the same method to be using 1, because it's not as hard as well. Something we can check for 2 is when A equal 1. When A equal 1, we can see that we don't really care about B and C, because 1 over A is already 1. It is already larger than 1. And one thing before we look into this typical question, I want to make you aware that whether it is a equal sign here is extremely important. It's very essential. Okay, let's go. So when A equal 1. So the sets actually already include what we get for question I. For question I, we find the sets that satisfy the equal sign. Now we just add something should be larger than the larger set. Okay, so let's go. So for A equal 1, actually we have something more, because in previous questions, when A equal 1, it doesn't really work. But for question 2, when A equal 1, B and C can be literally everything. So we actually have A, B, C equal 1, B, C. So let's write like this. And let's look at A equal 2. So if we want, so we can do question 2 based on what we get in question 1. If we want the left-hand side larger, we can actually make BC smaller, so they will be bigger. So we have 2, 3, 6. We have these 3. Remember, we still need A is smaller than B, B is smaller than C. Everything, at least we know, if we set BC that is smaller than the equation set, they are going to be larger than 1, of course, because they are on the denominator. So we can just set, without any worries, that B equals C, so 2, 2, 2, of course. We can set 2, 2, 2, 2, 3, 2, 2, 4. And in fact, we notice that 1 over 2 plus 1 over 2 is already 1, so we can set anything for C. This is very important, keep in mind. So when we are looking at 2, 3, so we only have to keep C smaller than 6, smaller or equal than 6, but larger than or equal than 3. So we have 2, 3, 4, 2, 3, 5, 2, 3, 6 is just the same. Let's look at 2, 4, 4. We skip for B equal 2. B equal 3 is still the same. B equal 5, it just doesn't, it cannot fit our requirement. And for 33, we don't really have any room for this kind of method. We don't have any rooms for us to do sort of inequality. We don't have any room. It's still very tight because A equal B equals C. The room is no room is left. So in the end, what we have is A, B, C. So we have this general term would be 1 B, C can be anything, can be 2, 2, and any C. It can be 2, 3, 4. It can be 2, 3, 5. And all the solutions here, actually, because since they are, as I said, they are in the equation set, and of course they are in this set because there's an equal sign. That's the end of the solution to problem 1. I hope you enjoyed that. I thank you for your listening. I know this solution might be not that mathematical, but it might be helpful.